In this second portion of the lecture for Class 1 in summer 2020, I'm going to introduce you to some of the computational tools that we want to use throughout this course in order to visualize what's going on in our quantum mechanical systems. Very frequently, quantum mechanics is a little bit anti-intuitive, and it's really good to have techniques that you can use for computing the results and then thinking about what those results might mean. The particular computational tool that I'm going to be using throughout this course is going to be NumPy as a library of routines within Python. There are a lot of others, and the tool that we'll be using in order to see what's going on and to describe what we are doing computationally will be the Jupyter Notebook. Jupyter Notebooks permit us to combine text and formatted equations and code all in one source so that we can write up what we're doing and do computations at the same time. We're going to use throughout the course NumPy and Jupyter Notebooks to visualize quantum mechanical results, so we need to be able to plot and compute. And then I'm going to introduce you in this class to one particular tool that was written by a student of mine several years ago that is very good for figuring out what's going on in one-dimensional systems so that we can do calculations. I've mentioned a little bit of our motivation for doing things this way. The primary motivation is actually going to be that the fact that most problems in quantum physics can't be solved in closed form. This is also true of theoretical mechanics and other courses where you learn about all sorts of closed form solutions, but then in the real world, the situation is not quite so straightforward and closed forms are not possible. It has become the fact that most modern physics, by modern, I don't mean, a modern physics course like this, but I mean most real modern physics in research is done computationally, that closed form theoretical solutions cannot be found. Closed forms can be used in order to get an idea of how a system should behave or why it behaves in a certain way, and then the actual results have to be done numerically. So as I've mentioned, ideal cases and closed form solutions do give insight into what's going on, but they don't really come close to reality. We'll talk a bit about that later on. And our approach of computation and plotting can frequently yield new insights into quantum mechanical problems. The tools that we're going to primarily use in this course I have mentioned already. The NumPy library within Python. So NumPy is a MATLAB-like open source library in Python that allows us to perform very efficiently both simulation and modeling tasks. And perhaps most important to me is that once you know how to program in almost any language, you can figure out how to do things in Python pretty quickly. And in particular, there are a number of very good tutorials and examples and libraries that are available to us. Online help for this is actually very good. The two sites that I use most frequently are scipy.org and Stack Exchange, but more frequently than that, I just Google what I want to do with this catchphrase NumPy, and within the first 3 or 4 things that are returned, I get a way to do it. Maybe the principal idea to know about NumPy is that NumPy works with numerical arrays. And by that, I mean, for example, a vector. They could be multiple dimensional, but one-dimensional array would be potential 1, potential 2, potential 3, potential 4, basically. So each term would be a different potential, and I could have an array that forms a potential as a function of position, for example. And then some other variable, a, which depends upon position as well. And a nice thing about NumPy is that it defaults when you write something like v times a, v asterisk a, it defaults to multiplying v times a as a term-by-term multiplication. So let's say let's call it w of I is equal to v of I times a of I. And it just takes each of the corresponding terms, multiplies them times one another, and creates a new array that has the same index. Right? It can also be instructed to carry out other multiplications like dot and cross products and matrix products, but we won't need to worry about that much in this course. All right? We're just going to be doing basic mathematics in this course, basic arithmetic almost. One other separate library that is quite useful to us, so there's the NumPy library. Another library that is useful to us is the plotting library that I call matplotlib. All right, and you can make everything from simple linear plots to bar charts to two-dimensional plots and representations of three-dimensional objects. Using matplotlib, you can even make videos. But again, we're just going to do some very basic plotting with matplotlib. Maybe what I should say here is that I am by no means a programmer or a coder, but I know what I want to calculate, and I know about 10 commands in Python, and those 10 commands enable me to do almost anything that I want to do, as long as I can look up the functions that I might want to do my calculation on. And for that, in a couple of slides, I'll give you a site that you can go to that's just got a list of all the mathematical functions and how to use them in Python, actually in NumPy. So today I'm going to talk about two specific examples. I am not going to go through every detail of these calculations. I'm more or less talking conceptually and about a big picture as far as this is concerned. And then the specific example can be found in examples that we've actually put in LMS for you. And homework 1 actually involves you going in and working with the example program that we give you for plotting a wave function and the example program that we give you for doing a calculation to find a wave function. It's a specific technique called the shooting method, which I will go through in a little bit more detail after this. But as in many things, the primary way to learn about this is by trying it. You do it, you make a mistake, you try again, you make a mistake, you try again, and as you proceed, you learn quite a bit about the way that the programs work. And hopefully, by the middle of this course, you will be a successful 10-command Python programmer, and by the end of this course, you'll be looking at the things that I've written, and you'll be saying, well, that's awkward. I could do a lot better than that. But again, my goal is not to turn you into a coder. My goal is to give you tools that you can use for understanding quantum physics. So plotting a wave function or a function in Jupyter Notebook involves two steps. One is defining the thing that you want to actually plot. And in order to do that, you have to create an array. And I'm going to function on I'm going to focus on one-dimensional arrays or vectors. One way to create an array is to define it term by term. So that's what I have done here. And generally, you don't want to do that in computational physics. But the array, the vector, rs, is given by, now over here, what we've done is to specify that the numbers that we're putting in here should be interpreted as an array of numbers. And I've used a shorthand. NP stands for NumPy, and in the first program that you'll work with, you'll see that we sort of shorten what we have to type by defining NP as meaning NumPy. And then the object that we're creating is an array. So NumPy array. And there's some syntax that's got to follow with brackets and parentheses, all right, that allows this to understand that this is an array which is oriented in a particular direction. And the 0th element of the array is 0.01. The second, the next element is 0.02, 0.03, 0.04. So there's our array. NumPy defines the first element of the array as the 0th element of the array. Or more typically what we'll be doing is creating an array using this command here, NumPy arrange a range, right, which runs from 0.01 to 100 in a step size of step r. So it's first term, last value, first value, last value in steps of. So there are 10,000 steps from here to there, or 9,999 steps from here to there. Okay, and that has now created an array which is rs. And then, I know this sounds pretty trite here, but you decide what you want to do and then look it up. Usually I'll just Google something like NumPy mathematical function, NumPy multiply, NumPy exponentiate. You know, just Google that, and that typically works. Or you can find an entire list of all of the functions, of many of the useful functions here. Okay, so that's as much as I'm going to tell you about. So here's a specific example in which we calculate the hydrogen wave function and plot it. Once again, r sub s is some scaled radius, some distance, which we create by making a NumPy arrange a range, which will be an array, a vector, that goes from 0.01 to 100 in steps of 0.01. And so 10,000 steps. The calculation goes relatively quickly in any case. I'm going to do something a little strange here with respect to scaling, in that we're going to rescale r so that it actually is in meters. And by the way that we're going to do that is by identifying the Bohr radius, A0. So A0 is 0.53 times 10 to the minus 10 meters. And we'll use A0 later on directly in the calculation for the normalized wave function. And then a little bit of a strange thing here is that we're defining the radius in terms of meters again. So we're taking steps of a 0.01 Bohr radii, where the radius is in meters, right? So we've scaled r, so the actual vector r is in steps of the Bohr radius, and it's of order 10 to the minus 10 meters. Define a constant. And then the funny thing that I'm going to do is that very frequently in the computation, the important thing is the radius measured in terms of Bohr radii. So I'm actually explicitly dividing it back out. And so R over A naught is a quantity which actually is R sub S, but it's more specifically a scaled radius. So this is a radius in meters, and this is a radius scaled in terms of Bohr radii. And R over A naught is actually the same thing as RS. So it's a little bit counterintuitive there, but I did that so that we could explicitly see what it was that we were working with. Now, the functional array psi of the 100 state, so the ground state of the hydrogen atom, is appropriately scaled. Now here's a function, numpy square root. So what you would do if you wanted to find that command is actually look at the site that I just gave you, or think about how you might command it in Excel and give it a shot, see whether that works. Or look here, you find it there. So scaling 1 over the square root of pi times 1 over the square root of a cubed. So one difference between LaTeX and the commands here is that in order to exponentiate something, you put a double asterisk. So a naught cubed is, or square root of a naught cubed, is double asterisk 3, right? Then we want to exponentiate something, so numpy e to the r over a naught is the next term in the wave function. So this creates an array, psi 100, which each term of which corresponds to each of the terms in r over a naught, which corresponds to each term in r, which corresponds to each term in rs, which was the original array that we created. So all the calculations are relatively straightforward. I could have written this with fewer steps, but I wanted to be explicit about what the measures were that we were actually using. Now we want to plot this, and we're going to create figure 1. I've already instructed above, I haven't shown you this, we will in the example, that matplotlib be included in the libraries that this particular Jupyter notebook would access. So these commands are related to matplotlib. In figure 1, we're going to plot r over a naught versus r over a naught on the independent axis versus psi 100 on the dependent axis. So psi 100 here, r over a naught on the x-axis. So the distance measured in Bohr radii. In this particular case, I set the axes. X goes from 0 to 20, and y goes from minus 10 to the 14th to 10 to the 15th. The reason these are so large is because a naught cubed, or rather a naught is such a small number, right? And then u would be expected normally to include your units here, right? So I've put labels on these, but these labels are not actually satisfactory. But this is the set of commands that you would use to make an XY plot, okay? Jupyter Notebooks also allows you to do LaTeX style editing and text editions. So you can create text cells and code cells and plots all in one document. And in order to explain what you're doing, it's very nice to be able to use formatted text. The approach that is used for the formatting in a Jupyter Notebook is called Markdown. And Markdown is an HTML environment, right? It uses many of the formatting and mathematical commands from LaTeX. And the mathematical formatting language that I use in Word is also very similar to this. So normally I just guess, oh, here's what it might do, and then I see what it actually makes. The set of commands here, double dollars, enclosing something in double dollars, actually sets an equation across apart on a separate line. And I want to make the Greek letter psi, and so it's \psi. I want subscript, so sub 200. I bracket it in order to force it all down. What was created here isn't exactly what this is. This would be 1/4 square root of 2 pi, and it would actually be in the ratio. And the way that I formatted it here using Word, Microsoft formatting is a little bit different. But this set of commands produces that, and you can go through and sort of make sense out of each of those steps. And the language is very similar to what you may have already used in equations in Word. So you can add these things as text above or below your code. All right, now for the specific example in which we're going to solve for a wave function under certain circumstances. This is the numerical solution to the one-dimensional time-independent Schrodinger equation. In the case where we have bound states, we'd have to write the code somewhat differently in order to solve for free states, in order to solve for propagating wave functions. Bound states allow us to use a particular approach, which is called the shooting method. And we need to use a more like a matrix-based approach to find coefficients for propagating waves. So we're going to concern ourselves this time around with solving the bound states for specific bound states of the Schrodinger equation. In order to do that, we have to rewrite the Schrodinger equation in a way that allows us to take a starting position, a starting value, and iterate outwards from that one or two starting values. Normally it's two starting values. So first we'll set up the Schrodinger equation. And again, we're concerned with the time dependent. But we'll start out with the entire Schrodinger equation with the operators, the Hamiltonian, and the energy. Writing it out in one dimension, h bar squared over twice the mass of the particle, second derivative of the wave function with respect to x, plus the potential as a function of position and time, normally, times the wave function, is equal to square root of -1 h bar d psi dt, the derivative of the wave function with respect to time. For the time independent case, the right-hand side just becomes energy, and in order for it to be time independent, we have to remove the time dependence from the potential. And then in order to actually do computations, what we're going to do is set the derivative of the wave function on one side of our equation and the kinetic energy on the other side. The kinetic energy on the other side. So maybe before we start, I want to review with you our understandings of the way that wave functions in one dimension, in all dimensions actually, behave. But in particular, we're concerned with bound states right now. And so here are a couple of things that you learned but may not have been explicitly stated in Quantum Physics 1. It's hard for us to include everything. So first of all, looking at this wave function here, for a bound state, the wave function envelope, that is the overall shape of the wave function, had better go to 0 outside of the well, right? And that has to do with the fact that the wave function's got to be normalizable, for example. And we also know that the wave function is going to decay exponentially outside of the well. A few other things that you should know in order to be able to look at and interpret things that you are seeing in wave function behavior when later on we actually solve for a wave function in a given situation. The wave function in classically allowed regions, that is where the total energy is greater than the potential energy, so the particle has kinetic energy in this range. Remember that the energy of the state is independent of position. Total energy is independent of position. The potential energy depends upon position, and the kinetic energy, which is the difference between the potential and between the total energy and the potential energy, depends upon position. When the kinetic energy is positive, or energy of the state minus the potential is greater than 0, that's a classically allowed region. And the solution for that particular situation is going to be what we call piecewise sinusoidal. That is, that in a particular region here, from here to there, the wave function is going to be simply sinusoidal. But then what we've got to do is match up the wave function at the boundaries with the decaying exponential or the other sinusoidal region. So here's one sinusoid due to that kinetic energy, and here's another sinusoid due to that energy, and then we've got to shift them around and vary their amplitudes in order to make everything match up inside and out. In the classically forbidden regions, the wave function is going to decay smoothly to 0 as what I'll call a piecewise exponential. So again, this was a piecewise sinusoid. Here's one frequency and amplitude. Here's another frequency and amplitude. Okay, piecewise sinusoid here and there. And out here, if I had steps in the forbidden region, I would see piecewise exponentials, which would be decaying at different rates in each of the different regions. But then we've got a few more rules that we need to apply, and I have a few of them on the next slide. So some quote-unquote intuitive rules for sketching and understanding, interpreting wave functions. 1. Solutions for the Schrödinger equation curve toward the x-axis in classically allowed regions. I'll show you that in a few minutes. So when the kinetic energy is positive, the Schrödinger equation curves toward the x-axis. I'll draw on that in a minute, right? And they curve away from the axis in classically forbidden regions. You'll see that the curvature switches sign, right? Not sign, but it switches its behavior with respect to the axis. 2. For bound states, the wave function's got to go to 0 for large distances outside the well. It's got to be normalizable. I mentioned that on the previous slide. 3. That curvature that I mentioned above increases for larger kinetic energies, or rather, not kinetic energy, larger difference between the total energy and the potential energy. Right? It will decay more quickly exponentially, or it'll oscillate more quickly if the energy difference between the energy and the potential is larger. One thing that you saw in the previous slide, but I'll show it a little bit more explicitly in the next slide, is that the amplitude of the wave function within the bound state decreases for larger differences between the total energy and the potential energy. Again, you'll see that in a moment. This is not a hard rule because it really does depend upon whether you've got positive or negative kinetic energy. Here's the one that you learned maybe as one of the first things in Quantum 1, is that the solutions have to be continuous and smooth if the potential has no infinite steps. Remember, an infinitely deep square well has got solutions that are for which the derivative is not continuous at the boundaries. But that's because we've got an infinite energy in the problem. If the energies are finite and the potential energies are finite, then the solutions have to be continuous and smooth. And then one last observation, the energy eigenfunctions have an integer number of antinodes in the classically allowed regions. So here's an example as I described. My total energy, so on the top, I've got a plot of potential energy and total energy. And so here's my total energy and my potential energy. Okay, and I've got a classically allowed region, which goes from here to here. So classically allowed in this region here. And in this region, the solution is oscillating, right? At each point here, the solution actually is a sinusoid. It's just that the frequency of the sinusoid changes steadily because the kinetic energy is changing throughout this region. So I've got an oscillating solution here. And this is the n equals 5 state. And we can tell that by counting 1, 2, 3, 4, 5 antinodes. The n equals 1 state will have just one antinode. All right, so there's my my wave function for this particular state. Outside of the classically allowed region, in the forbidden region, the wave function decays exponentially on this side and on that side, right? And you might notice here that you should notice, I'm going to clear my my materials here for a moment, that in these regions here, the curvature is curvature which is concave toward the x-axis. So for positive kinetic energies, the curvature is always concave toward the x-axis. And out here where I've got negative kinetic energies, the curvature is convex towards the x-axis. Convex, convex. And again, you can use these little cues looking at solutions to wave functions to figure out whether you're in a allowed region or not, because when you actually do a computational calculation, you might not know which particular region you're in, but you can look at the solution wave functions and come to some conclusions with respect to the region that you're in. So in terms of our list that we had before, the wave function goes to 0 out at the when we're outside of the well. I discussed the curvature direction here. The curvature of the wave function depends upon whether you have positive kinetic energy or negative kinetic energy. The speed of curvature, the magnitude of the curvature, tells you that sorry, let me think about this for a second. Yeah, the magnitude of the curvature tells you that this is a higher energy region here than this region over here, right? And we'll discuss later on the amplitude as a function of the difference in energy. And then we just discussed continuity and what I, for short form, call smoothity. That is the continuity of the derivative, of the first derivative, and the fact that we can count up the integer antinodes in the antinodes and figure out what energy state we are actually in. So that's the fifth state. And again, the ground state would just have one antinode. There's a little bit more that we can discuss with respect to solutions for wave functions under special conditions. Here, I have a symmetric potential. So let's say the 0 here is at the center, right? And my potential is symmetric about that center point. Then in that case, the wave functions will have the eigenstates rather will have very specific symmetries as well. The ground state will be an even function about the center with one antinode. The first excited state, this one here, right, will have a 0 at the center, and it will be odd with respect to reflection about the center. Okay, so I've got an even state here, an odd state, an even state, an odd state. And this can help us as we move to the next stage when we're trying to figure out which wave function we're actually trying to solve for when we do a numerical solution. I already showed you a little bit with respect to scaling for calculations. I want to, but we could have done the entire calculation directly in meters and it would have been okay. But sometimes we sort of get out of range capability and we run into problems with zeros and too big a set of numbers in our calculations when we're working in quantum mechanical quantities. So I'll just mention here that coefficient 2m over h bar squared, which appeared in the Schrödinger equation, is pretty big in MKS units, right? MKSA units. 2 times 10 to the 38th, right, for an electron in MKS units. And if I've got some problem where I'm going to exponentiate 2m over h bar squared or the charge on the electron, then I might find that I get an overflow or an underflow in my calculation. So we want, when we're doing computation, to avoid too big and too small numbers. I leave it up to you to decide what big and small is. I typically think of big as anything bigger than 1,000,000 and small as anything smaller than 1/1,000,000th or something of that order. But it's all a question of whether you have enough digits in your calculation in order to be able to have a reasonable idea that your calculation isn't going to go off because you've got an underflow or an overflow. So we try to keep the numbers within a reasonable range. The actual choice of scale is arbitrary. You can just choose things to make it work for you, right? Make your choice of scale fit your problem. Okay, now I want to proceed to the numerical solution of the Schrödinger equation as we had written before. So I'm going to, in order to do this set of calculations, and again, this is a choice, but I happen to like this choice, rescale the Schrödinger equation in order to rewrite it in terms of dimensionless variables. So we have a position, x. I'm going to create a new variable, z is equal to x over some scaling variable or constant, L. I'll talk about that in a minute. I'll create a new energy, epsilon, which is the ratio of the actual energy to some scaling energy, E0. And then I'll scale the potential as well. W is equal to the potential energy divided by E naught. Okay, we choose L and E naught for convenience of calculation and for trying to make the magnitudes work out and to perhaps understand what's going on. So we haven't defined those yet. I just know that that's a length and that's an energy. So I've rescaled everything to length and energy. And rewriting the time-independent Schrodinger equation that we had on a couple of slides back, I've got d squared psi dz squared is equal to, got a number in there, pi squared, right? V of x minus e over e naught. So I've just scaled potential and energy and rewriting that in terms of the new variable, pi squared w minus epsilon times psi. All right, now I want to convert this equation into a finite difference equation. So basically, all that we're doing here is employing Taylor expansions. All right. I'm going to, I have to convert my position z into a whole series of steps in z, all right, where in this case j is an integer and delta z is a step size. So the actual position is an integer times a step size. I integerize my wave function as a function of, it's a continuous function of position, but I chop it up into small steps, z sub j, right? Psi of c sub j, and I'll just call that psi of j. And potential as a function of continuous variable z can be rewritten in terms of the discrete steps z sub j as well. So I'll just call that w sub j. Okay, then in order to calculate the derivative, so let's say I've got a function, let me make a sketch of it here, that maybe looks like this. That might be what my wave function might look like. And I have the wave function here, and I have the wave function there. And then what I'm going to do is approximate the slope between those 2 points as the linear difference between the two divided by the distance. Okay, change in height over change in position. That's all that that is there. But I'm defining it as midway between the two here. All right, that's a finite difference approach, an approximation to calculating the derivative. And in order to calculate the second derivative, then I take the derivative at a point halfway above the point of interest and halfway below, half a step below the point of interest, which I just solved for above, divided by the distance between the two. And that allows me to get the second derivative. And plugging this into that, all right, yields second derivative in terms of the values of the wave functions at various points, that psi sub j, need my laser pointer, the second derivative at point j is equal to the value at point j plus 1 plus the value at point j minus 1 minus twice the value at point j divided by z squared after making that substitution. Now we plug that into our Schrodinger equation, and with some rearrangement, we get this relationship, which can be used if we know the wave function, if we know the potential as a function of position, and we know the wave function at point j and the wave function at point j minus 1, then we can solve for the wave function at point j plus 1, right? If we know two values near some point, we can solve at another nearby point. And then once we know j plus 1, then we can use that and J in order to solve for the next point and the next point and the next point. So if we can supply two guesses to start our calculation, then we can calculate the wave function everywhere. If we know one more thing. We know the potential, and we know our first two wave functions. We guess our first two wave functions. We need then to know what the energy is. There's only one parameter left in order to calculate the wave function at the next point. So the only parameter that we can use to achieve agreement of the wave function with expected behavior, I'll show you that in a moment, is the energy. A specific example here would be this one, to give you an idea of the scaling. If we have a finite square well of width L, then we expect the energies for that well to be of order h bar squared pi squared over 2m L squared, right? And so that would be a good energy to do our scaling on. The energy, this is the energy that we would calculate as the ground state for an infinite square well, right? Ground state infinite square well isn't going to be very different from the finite square well and finite depth square well. And so in order to scale things so that our energies are of order 1, it's reasonable to take that as our energy scaling. I could have chose something else, but this is an energy scaling that I can remember and that works. And I'll take a useful length for the problem to be L. As a concrete example, we take a finite square well, which has a side length, the region over which the potential is 0, is 10 nanometers. We'll take an electron, an approximate electron, 9 times 10 to the minus 31 kilograms instead of 9.11 something, right? But close enough. And then calculate the scale of the energy, and it comes out to be 0.00375 electron volts. We will take the depth of the well, so just in order to solve the problem. On the next slide, I'm going to take it to be 20 E-naughts, right? I wrote 4 here, and I forgot to change it, so I changed it in my calculation to 20, right? So the depth of our well is actually pretty shallow in terms of electron volts, but it's a wide well, 10 nanometers or 100 angstroms wide, right? So that's the problem that we're solving. To make a sketch, the potential will look like this, with the depth of about 0.075 electron volts and a width of 10 nanometers. And we expect that our wave function for this state is going to look something like that. All right, now we want to do our calculation. We already know that we can choose the starting point for our calculation based on symmetry. That is, if I have a potential well that is symmetric and looks like this, I've got a central symmetric point. My wave function's going to be symmetric about the center, right, as we discussed earlier. And that means that the slope at the center is going to be equal to 0. So I could actually start my calculation at the center and work out. Okay? So remember, what we're going to be guessing here is the energy of the state. We're going to be guessing the energy of the state. And we're starting with 2 guesses for what the wave function does at the center, and then we work our way outward. All right? And then we'll talk about the behavior in a minute. As I mentioned, for a symmetric potential, we can limit the calculation to one side from the center, okay? For the finite well, the solutions are going to be even, and that means that they have zero slope at the center. So as our guess for the wave function, we'll take, lost my laser pointer here, psi at the center is equal to psi one step out. Remember, that might be like 1/100th of a Bohr radius out, and we'll take them equal to each other. It's not, the actual magnitude is not important because we can normalize later on. Odd solutions, if I want to find the first excited state or the third excited state, are 0 at the center, redrawing here, well, state, all right, are 0 at the center, and they have finite slope. So in that case, we might guess psi 0 is 0, and psi 1 is some number, 1. All right, it's just got to be non-zero. And then we're going to find the energy that causes the wave function to behave the way that we want it to behave. And then we have actually found something close, an approximation to the eigenfunction. A spreadsheet example is here, right? That is that here are my positions and my potential. Remember, the potential looks like that. It's 0 at the center, and for steps out until we get to some point, and then we get to some point, let's call it the, I don't know, the 100th point, and at the 100th point, the potential takes a step up, all right? So that would be my potential, right? That's not an assumption. That's something that I'm going to put in to the problem. Now the assumption. If I'm looking for the symmetric state, the even state, then I'm going to assume that the wave function at the center is equal to the wave function a little bit away from the center. I make those two steps very close to one another, and I take them both to be equal to one another. 0 slope. And then for the next state, I calculate it based upon those two, and the next one, and the next one, and the next one, all the way out to some reasonable physical distance outside of the well. In Python, we might write the calculation like this. We're going to call a routine a function called the forward shooting function, and here's a little piece of it here. The input to the forward shooting function is a guess. Let's guess the energy, all right? Then, and that comes in from another section of the program. Then my psi of x, of I, let's call it psi of I, is I'm just going to fill the whole function up with zeros. So I'm going to make the wave function equal to 0 everywhere, initially. Then I'm going to put the first point in, and here I'll either put 0 or I'll put a finite number, f of 0. That comes from elsewhere, right? So this is one of my initial assumptions. And then I also need to calculate the next point out, or to make an assumption with respect to the next point out, all right? The next point out actually depends upon the slope, all right? So the way that I'm making my set of assumptions here is, let's say my wave function looks like this. Then I've just told it what the center is, f0. f0. And then I tell it what the next point is by giving it the slope at that point. If I set f0 equal to 0, df0 equal to 0, that equal to 0, then I'm setting the two adjacent points at the center equal to one another. My alternative is that so this would be f0 equals 1, and the other assumption here is that I would assume that that didn't work. df0 is equal to 0, zero slope. Okay, so that might be a set of assumptions that I make in here. That's my input. I'm seeking the symmetric or the odd or the even solution. My well in this particular case actually looks like this. Here's my potential. Goes to 0, crosses through, comes up the other side, like so. All right? And the solution that I'm finding here is actually the solution that would look like that. Okay. So now you might see that something really wacky is happening here. If I choose the wrong energy, and I will choose the wrong energy, then I start with my, in this particular case, I chose my odd solution, my first excited state, and then just allowed the algorithm to step its way out. All right? Finding the value of the function at each point for a given energy. So remember, we're putting the energy into this problem, and then we're computing what the shape of the wave function is. What we'll find is that sometimes the wave function will just go like that. It'll go off and grow. And sometimes it'll do that and go off in the other direction. Actually, it never curves that way. It always curves that way, right? So now let me erase my slide stuff here so that we can come back to what this particular solution. So for a particular guess, I put the guess in. The program went ahead and calculated the wave function that would result from that energy. And we see that for that particular energy, the wave function takes off when we get outside a certain region. By the way, if I'd only plotted this much, you would have said, good solution, right? And that might not be too bad a solution. But after you get outside a certain range, the wave function takes off, right? And so it means I haven't got the energy for this eigenstate quite right. What I want to do is maybe guess the energy a little bit closer. When I do that, it'll look like that. If I guess a little bit better, it'll look like that, and so on, all right? And so you just continue, and actually you can write code to do this. You continue to guess solutions until you find one which is 0 out to reasonably 0 out to an acceptable value to you, or such that you found the energy to within the range that you wanted to find it. It turns out that the difference between this energy and that energy, for example, is going to end up being in 10,000ths of electron volts, maybe millionths of electron volts. And so we've actually, with this particular solution here, found an energy very close to the actual energy for this particular well, right? So just to reiterate, my well in this particular case is taken to be shaped like this, right? And the potential is drawn here, okay? The actual energy of this solution is plotted here. So there's the energy that was guessed in order to get that particular result. If I wanted to change the shape a little bit, I would change the energy and just keep iterating, keep guessing until I get something that is satisfactorily close for me. Okay.